There we go.
Yeah, now you're good.
Okay.
Good
Good.
now. Yep.
Good. Okay, so now, and other than just kind of make list of knots by crossing number, we can look at families, twist knots, Taurus knots. So here, now I can't go down. Let's see. Okay, so today I'll figure out what I hit. Okay, so today I'm just going to talk about a tabulation of Legendrian knots and links, in particular Taurus links. Okay, so today I'm working in the standard contact structure, so R3 with a standard contact structure. So it's just a field of planes. So these are maximally non-integrable planes. And inside this manifold, so the importance of manifolds are Legendrian curves. So these are always tangent to these planes. So feel free to ask questions. I don't know a lot of you, so I don't know what kind. I know symplectic geometry is very big nowadays, so feel free to ask questions if anything is not clear. Okay, so in particular, if I looked at, let's see if I try to use my pointer, like the x-axis here, this would be a Legendrian curve, or this is the y-axis, those would be Legendrian curves. If you draw it this way, it looks really hard to construct Legendrians, but in fact, it's really easy to construct Legendrians. I'll often be talking about this front projection. So this is in the XZ plane, and you have these things that have cusps on them. So cusp curves in the plane without vertical tangents, you can lift to 3 space as long as you use the slope as the third coordinate. So instead of this is just an XZ, we make it into 3 space, adding the slope. And the nice thing about this, if you're used to low dimensional topology, you always have to be so careful to say which strand is over, which strand is under. But because of our third coordinate is slope, we don't have to do that. So anytime I see this, again, at that crossing, this has y = 1, this has y = -1. And to keep a right-hand coordinate system, positive y is into the board. So that's why every time you see a crossing, it really looks like this. Positive y is into the board, yeah. So x, y, z is, yeah. So that, especially with, yes, positive y is into the board. So like here. Okay, so in fact, Legendrian knots are so abundant. So you can take any smooth knot or any link type, it'll have a Legendrian representative. And in fact, not just one, but an infinite number. Okay, up to Legendrian isotopy. So we're interested in, if I have a Legendrian unknot, or I have 2 Legendrian knots, I'd be interested in getting between one to another by a 1-parameter family of Legendrians. I mean, kind of respecting the geometry at all times. So in fact, there's 2 classical invariants known as the Thurston-Bennequin and rotation number. So here's just an example. If you do Legendrian unknot, so an unknot is just like a circle you can think of as in the smooth world. These are all Legendrian, but they're different Legendrians. Okay, so they're all Legendrian unknots, but they're different Legendrian unknots. So you can see this by the classical invariants. So here, so the TB is you can count it very easy from crossings and doing combinatorial counts of the cusp. In this projection, this is just a different projection of it. You would just do its ride. So for every crossing, there's an orientation. You can figure out the sign of the crossing. The R is kind of like a rotation number in these projections. So these are all, so even for an unknot, there's an infinite number. So it sounds sort of hopeless. I mean, so now, instead of like the very first slide where I was talking the low dimensional topology, where they try to make a list of all the smooth knot types. Okay, we have to narrow our scope. So we're just going to fix a knot type and just try to understand all the Legendrian representations of that knot type. Okay, so we fix the smooth knot type and we try to understand all of them. Again, up to Legendrian isotopy. And sometimes we can do this, okay? So for example, we understand all Legendrian unknots. So this is kind of funny to me. I mean, it's like it's like 25. We've only really understood Legendrian knots for 25 years, compared, I mean, it's like basic stuff, like basic knot shape is the unknot, right? So this is due to Eliashberg and Fraser. So how we kind of understand and kind of organize it. So even though there's an infinite number, we want to organize all this set so we kind of understand it. And I think of this as like a family tree. Okay, so it's just a graph. Mathematically, it's just a graph. But I think of this as like this is a family tree where you just have one ancestor. So this is the most important one. And then all others are obtained by just adding these zigzags. This is like a down zigzag. This is an up zigzag. If you were to look at it in a different projection, you would see like there was more curly Qs. Okay, so you can't just get rid of these curly Qs. Okay. So usually, this is the idea. So you can kind of see this as like a graph with a single peak. We tend to draw this instead as just the shape here. So we represent all the Legendrian knots by this graph. Sometimes we call it a mountain range. Sometimes they call it a tree, family tree. Just so the idea is, if you really have to understand the very top mountain peaks, and then everything else just get by zigzags. So even though there's an infinite number, the structure we understand. So we label the position in the plane by TB and R. These are always going to be symmetric about R equals 0. But the heights might change, so that TB. Right, these are not, so these two are, so these different vertices are not Legendrian isotopic. So every vertex is representing a different Legendrian knot. And this is like two vertices are connected if they're just as one is obtained by a zigzag. And of course you can do the zigzag and then you do a whole bunch of moves so it doesn't look like a zigzag, but up to isotopy, it would have to be equivalent to this. Okay, good. This is important to make sure. Okay, good. Yeah.
So is this just like exactly the set of things that satisfy the obvious?
Right. Yes. So here, there's classic results that say that the TB for the unknot, and that's a really interesting area where you fix a knot, you figure out for every knot type, there's going to be an upper bound to TB. And so for the unknot, it's -1. And this is kind of saying, so, well, in this case, this is kind of more obvious, but we'll see other cases where TB and R alone are, like the max TB is not going to tell you the shape. Okay. Good questions. Okay, so unknots we understand. Woohoo! Okay, so the unknot is an example of a Taurus knot. So a Taurus knot, these can just be drawn on an unknotted solid torus. So here you kind of go around. Again, there's no intersections. It's just kind of like a pattern. You make it by putting them on a torus. Yeah, on a solid torus. Yeah. So, so on a two torus, on the boundary of a solid torus. Yes. So this is kind of, maybe here you can think of them. My necklace is a 2-5 torus. Okay, so the idea is, you're kind of going in and out of the hole and kind of around these strands here. Okay. So in general, these are kind of a classic family. So usually they're labeled by 2 integers, P and Q. And so there's various conventions. I'm always assuming that P is less than or equal to Q, but I'll do plus Q or minus Q. So this kind of depends on which way you're wrapping as you go, like in this kind of twisting strand right here, clockwise or counterclockwise. Okay, so again, we just kind of put the torus there and draw it on the torus, but then the torus disappears and we're just interested in the knot. We can move it however we want. And in particular, this will be important later. If P is equal to 1, then it's just an unknot. Okay, so. Nope, they're just, no, P and Q are just integers. Oh. Oh, yeah. So the plus or minus depends as you're kind of going around. Oh yeah, I guess you could kind of think of well, sort of like it's a twisting here. Whether you like standing on this side, I'm kind of going that direction versus this direction. Yeah, you could see it also in terms of if you oriented it, the crossing numbers are the crossings positive or negative. Yeah. Good. Okay, good. So we can take one of these Taurus knots and we can try to do the same thing for the unknot. We knew we could understand all the Legendrian representations of it. And for the positive trefoil, and actually all positive Taurus knots, we can similarly understand. So the positive trefoil, here's just an example. The positive trefoil, it again looks like the unknot, sort of. It has a single mountain peak, but it's shifted up. So the unknot had the height at -1. This positive trefoil will have height at 1. So this is a classification due to Etnyre and Honda. So the idea is, again, if I know the shape at the top of the mountain peak, I know the shapes of all the different ones. And every vertex is a different Legendrian positive trefoil. So this is just the 2-3 Taurus knot, but in fact, all the P plus Q ones will look similar. There's always going to be a unique peak, but it'll be different. It'll be PQ minus P minus Q. So the height of that mountain will change, always centered at R equals 0. And again, just to emphasize, every vertex represents a distinct Legendrian representative up to Legendrian isotopy. And 2 vertices are connected by an edge if they are related by this stabilization. Now, so maybe every knot type has this like kind of simple mountain, and we call this mountain range. It's the idea again, there's always an upper bound, and we figured this out. But then, yay, something interesting. So for example, if I do the 3-7 Taurus knot graph, mountain range, it's going to have 4 peaks. And so I've just drawn the figures that correspond to the 2 peaks on the right-hand side. If I reverse the orientation, I would get the ones on the other side. Again, reversing the orientation will change R by a minus. Right? Right. Yeah, the previous page was Q positive. So as long as Q is positive, it'll have a single peak. But when Q is negative, or when I put a minus sign here, it'll never have a single peak. Okay. Okay, maybe P equals 1 or something, yeah, except when P equals 1. So there's always these special cases. So in this case, I have 4 peaks, but in general, if you look at this fraction minus Q over P, and you sandwich it between integers, that's telling you how many mountain peaks you'll have. Okay. So, and we know what the max TB is. Again, we know that height of that mountain peak. And you get, yeah, you play around these P's and Q's. In this case, you can get really interesting mountain range. You know, sometimes the peak height, you know, like this depth of the canyons at the top can really vary. Sometimes between some, it'll go really down far, and some, you know, so really interesting mountain range shapes depending on Q and P. Okay. Yes. Yeah, there's a nice formula exactly from P and Q. It takes like a couple second a minute calculation to figure out all the peaks. Yeah, simple. Yeah, that's what's really nice, right? So so basically we understand all the PQ Taurus knots because given the P and Q, I can write down the mountain range pretty easy. Okay, in some knot types, there could be. And then I would draw that like as 2 vertices, kind of like side by side. But in this one, we call it simple, meaning that there's each of these positions is only 1. So this is saying that TB and R uniquely determines the Legendrian knot type. But that's a good question, yeah. But that's interesting. In different knot types, you sometimes get multiple vertices at different points. And then, yeah, interesting. Sometimes multiple vertices, they're distinct here, like lower down, but then they become the same the second you stabilize. So yeah, so for example, those are what we call simple Legendrian knots. So like the Taurus knots, knots, figure 8 knots. There's probably more that I'm not remembering, but it's not, I mean, there's a lot we don't know. Okay. Okay, so we did like smooth Taurus knots, and then we did Legendrian Torus knots. Now we're going to do smooth Taurus links, and then we'll talk about the Legendrian Torus links. So now we're moving in. So before P and Q were always relatively prime. So now I'm going to look at something like a 4-6 here. So I always write 4-6. I would factor out the 2. I think of this as 2 times 2, 3. So the nice way, that's telling you that it's a 2-component link, and each component is a 2-3 Taurus knot. So it just nicely works out that way. So in general, yeah. And again, you could do Q is positive or Q is negative, depending on the twisting there when you get in that strand. Okay. So the goal of the project is to understand all Legendrian NP plus or minus NQ Taurus links. So again, understand this. There are an infinite number of representations. How do we even like represent? So we know how to represent a Taurus knot as like a vertex on this mountain range. How do I represent a link? How many ways can I represent it? And there's just lots of really interesting questions. So that's kind of like the intro. So here, I'm just outlining the rest of the talk. So I'm going to talk about the classification statements. That'll take, just to understand what it means to understand all these links. I'm going to talk about how some of these results extend to cable links. And then I'll end by talking give you a flavor of some of the proofs. Okay, everyone good? Okay, so let's start about the statements. So first you have to kind of understand like realizability. So remember, if you have let's just take this, a 4-6 Taurus link, it's 2 components, each of which is a 2-3. So I'll just draw the tree for the 2-3. This is the mountain range for the 2-3. And then I can ask, well, can I realize a 4-6 using those 2 components? Those 2 vertices, which means each component would have those TB and R values. Or if I did a 6 minus 14, same question. Can I realize it using 2 components with those TB and R values, those shapes? Okay. So for example, this one you could realize, but this one you cannot. And so the theorem says that if you choose 2 vertices, okay, so you can realize this NP-NQ if and only if the 2 vertices have a common ancestor. So over here, I can't, ancestor just means go up, left or right up. But here, they don't have a common ancestor. These ones do, but these ones don't. But on the positive side, you could see that you always will, right? Because it just has everyone has the same ancestor. But if I take those 2 pieces, those 2 components could realize. You could construct a Taurus link using those 2 components. And this is where either you're a positive. In the negative case, I'm assuming that P is not 1. Okay, so I have to do a little bit different when P, I'll say this is what the statement is when P is equal to 1. Mm-hmm. But again, yeah, that's a problem. You can make an unlink with these 2, but they have to be intertwined. So when you make these PQs, yeah, they have to be smoothly, they just have to be the link. Yeah, it seems weird, right? Is that a condition on the linking method? Well, No, I mean, in some sense, that's just a topological thing. So the linking number is kind of forced to you by the topological type. But yeah, but in some sense, yeah, it's a little strange, right? You can always make but that's not a torus link. Yeah, so the torus link has to have, yeah, the linking numbers and things between the components, yeah. And the max TB reps, they're kind of like you have to take an n tuple. So often what we want to, just like for knots, you want to know what's the max TB, you know, like the height of the mountain. So for links, you would want to know what's the max TB, meaning the max, the sum of the TBs of the components. So here, if you just take the peak of the mountain n times, that will give it to you. When p is equal to 1, okay, so when p equals to 1, so that means each component is just a knot. But say I want to make a 2 minus 4 link, again, they have to be intertwined in a certain way. You could ask, well, could that be realized? And that is no for those two. But these ones you can realize. So this is like this we think of as a 2 copy. Okay. So this is like a 2 copy of a TB minus 2 unknot. The same thing, that's a 2 copy of a TB minus 2 unknot. Here's a 1 twisted 2 copy of a TB minus 1 unknot. So you get this kind of really interesting. So it's not at all obvious when you do this where the components are just unknots. Yeah, so the previous theorem was where p was not equal to 1. This is where p is equal to 1. So this is still the negative case, but with p equals equal to 1. Mm-hmm.
So, okay, so you're moving around these like lattices,
Mm-hmm.
positive and negative stabilization,
Right.
right? So are these all, everything you're talking about, are they all simple? Are they all simple? Like
oh, that's the next question. First, just can you realize? You mean simple in the sense of, yeah.
So here are we asking, I mean, is the realizability question like, can I always realize this combination of Thurston-Bennequin
yes.
numbers? Okay,
yes. Yeah. Can I realize this combination of Thurston-Bennequin numbers for the components? Okay. And here's a picture. Okay, so here I'm drawing the pictures. So like up there that they correspond. So it's that combination of TB and R. So, and in fact, this is just a 2 minus 6 torus link. And so you can see, so Ipsita, that's kind of like what you were saying too. You know, it makes it a little bit more concrete that, yeah, you can't always, yeah, you can try to put them together, but they won't be the right knot. Yeah, right link. Yeah. So these are kind of like the ancestors. So everything has to destabilize one of these ancestors. When you do 3, n equals 3, so if you do 3 copies, then it's similar. So, but the 2 other ones, so like I can make 1 of these and 2 of these other ones. I can't do 2 at the top and 1 at the bottom. So it's tricky in terms of the combinatorics of what you can do. Okay, so maybe this was your question. So like here I'm just saying which pairs of vertices can be realized, you know, so, but then you could say like, well, how many ways could a pair of vertices? Is it sort of simple? Like Hannah's earlier question, you know, like every vertex was just here. So you could say, okay, so I know that the red pair I could realize 4, 6 with a red pair, or maybe there's another green pair, you know, like another one where they both have the same TB and R, the 2 components have the same TB and R, you know, of those numbers. Are they necessarily isotopic? And yes, okay, so in some sense we have a simplicity statement. So if I have an n tuple that represents at least as an unordered pair, okay, there's a more subtle question when you talk about the ordering of the components and you're using one vertex more than one time. Okay, so again, so this is at least a way to represent the Legendrian Torus links, right? We just represent them by tuples of vertices, and every tuple that can be realized realizes at most one Legendrian Torus link. Yeah. Right. That's a good question. I mean, I don't know. I mean, for our case, when we're doing Taurus knots, the Taurus knots themselves are simple. So each position in the plane only has one vertex. But there are different knots that have more complicated mountain ranges. And so, yeah, I don't know of any example, but that could potentially be true, that you could, do it with one, but not the other. Okay, is this sort of clear? Okay, so the third question is sort of like symmetry. Sure. Uh-huh. So if you have one rep, you can always like stabilize it. Like if I have like the green, I can make another green with another link with using this component and this component and this component. So there are ways to kind of, change, but that's not the same. Those are different links because the TB and Rs of the components will be different. Okay. Okay, so we knew that now, okay, so far we know how to represent it, as unordered links, kind of as these n tuples. And now you can think of a symmetry question. So if I have one vertex chosen, for example, 3 times, you could ask, can I permute the components? So in the smooth world, if I have this torus link, you can arbitrarily permute the components. You just kind of like lift one of the components around and slide it over and push it down. So you can do that. And then you can ask, well, can you do that in the Legendrian world? Okay, so here's just a picture, for example. Could you do a cyclic permutation? So this would be an example of a 6-9. So you could ask, can I do a Legendrian isotopy, take the black to the red, to the blue, to the back, just kind of do the cyclic permutation? Or could you do a non-cyclic where the black goes to the black and the red and the blue are interchanged? So sometimes you can arbitrarily permute and sometimes not. So for example, again, all these things about the torus links they're always joint with Jen Dalton and John Etnyre. So cyclic permutations always produce equivalent things. So you can always do cyclic permutations. By Legendrian isotopy, right? By Legendrian isotopy. So non-cyclic, if you're in the positive torus link side, so positive torus links, there's lots of flexibility. You can produce equivalent ones. For the negative ones, if you're not at the very top, if you're not the max TB, you're not at the mountain peak. So say I've chosen that vertex, which is not at the mountain peak a number of times, I can do any permutation I want. But if you're at the mountain peak, you cannot do any non-cyclic permutation. You can only do the cyclic permutations. So this extends work of Mishichev. This was one of Eliashberg's students a number of years ago. So let me just kind of say, so that was where, and remember that p equals 1 case is a little bit separate. Here would be a max T. These are both ancestors. So every link will destabilize to one of these. The max TB, you choose a vertex, the same vertex. This is a non-max TB. So for the max TB, You cannot do any non-cyclic permutations there. But the non-max TB, I could do any, again, I could do, it only makes sense to do permutations when you're using the same because you want invariant preserving. So I could do any permutation I want for the components that have those TB and Rs. So again, this is a result of Mishichev, the max TB one. I know, but when p equals 1, no, that's where it's, yeah. So that has max, yeah. So when p equals 1, this becomes the max TB. It's strange. And it's basically, because the Q is 2, it's kind of on the second row. So the max TB ones have that n times or these kind of like twisted n copies. Yeah, kind of like split. I know there's like so many subtle cases, right? Okay, it's making sense a little bit. Okay, so we actually extended this using cable. These results actually extend to cable links. So torus links are cables of the unknot. So the unknot forms this unknotted torus. So you can fix another knot type and kind of do torus knots or torus links around that torus. So let me just kind of, I won't go, it would take a lot of slides to say it precisely, but basically we have, if it's simple and uniformly thick. Okay, so let me just do some examples. So for example, if K is a figure 8 knot, or if it's a negative torus knot, then basically we've been able to classify all of these, all the Legendrian cables of all of these cables. Yeah, so uniformly thick. This is something, it's kind of a little bit more geometrically nice. It kind of means that if I take a knotted torus in a certain knot type, it kind of says that the torus can be expanded so that it has a convex boundary in a nice form. So it has, yes, in convex boundaries, it means that it can be expanded so that the dividing curves have slope of max TB. Yeah, okay. Good. Okay. But what this really comes down to, what the statement of the theorem is what I want you to take away is like, if I know the mountain range of K, and then you give me a P and Q, I can completely determine the mountain range of all the NP and Q cables. Okay, and I know exactly which permutations can be done and which ones cannot be done. So basically, we understand all of them. In this case, I mean, K has to be simple and uniformly thick. But just to illustrate it, okay, so here's like a cable. So my knot I'm looking at is a figure 8 knot. The max TB of that is -3. And so when I'm looking at the cables, the classification, so it depends on whether that slope is equal to the max TB of the base, like your core, greater than or less than. So here's an example of an ancestor of a 3 - 9 torus link. Okay. Here's an example of an ancestor of a 6 - 15. So this is greater. So the slope here is greater than -3. Here the slope is less than -3. So in all these cases, these are just examples of ancestors. And what we find here, when the Q and the P, the ratio is greater than the max TB, you can do any permutations. Here we can't, no permutations. When you're really when you're equal to the max TB, no not cyclic, nothing, okay? Here you can only do cyclic down in this case. Yeah, the slope is, okay, so you fix the knot K, and then P and Q, you kind of do your like torus around a tubular, so you use that knot as the basis of your knotted torus. And then the Q and P are similar to before. You kind of have meridional and longitude. Yeah, the slope is just Q over P. Yeah. Yeah, sorry. Yeah, slope Q over P. Yes. Right. So like P is kind of like the number of like going kind of going around, right? Yeah. Mhm. Okay. So maybe I'll just use my last minutes to, and again, this is just an illustration, but the idea is that whenever K is this, simple uniformly thick, we can do this, right? Right. It kind of makes you a little dizzy with the pictures, but okay. So the last minutes I'm just going to spend just talking about some of the proof ideas. So this is a, so I just got to, this is a project that I've been working on for a long, you're all so young, it'd probably be hard to imagine, but off and on, I've been working on this project for close to 15, 18 years, so not solidly, like work on a little bit and then drop it, stuck, pick it up again, new idea, drop it. So it's been, it's really been an interesting thing that, because we're trying to do it for all P's and all Q's and all N's. So I just wanted to say how, if you're just interested in some cases of P's and Q's, there's different techniques that will work. So for example, if my P is 1 and my Q, and I'm looking at like a 1 minus 1. So both P and Q are 1. That's something you can prove, like non-cyclic permutations are impossible. You can do that just using fairly elementary techniques of generating families of functions. So it's just Morse theory. And well, it's just an outline. So a long time ago, in 97, I proved this idea that there's these link and you can't swap the components here. Okay, that's in the one jet space of S1. Yeah, for the Legendrians, right. So there's a way to, again, just give you an overview, but just, so you can show that these two links are different. And then Mishachev realized, and Ding and Gyges kind of wrote this up more precisely, that will actually imply that you cannot do non-cyclic permutations of this unknot. So this torus link. So if you wanted to just, if you're only interested in that torus link, you don't need very sophisticated machinery. If you wanted to do, okay, so now I'm keeping P equals 1, but I'm going to let more Q's. So again, each component is an unknot, but these are like what we often call n copies of an unknot, TB minus Q unknot. And Mishachev did this. He showed that non-cyclic permutations are impossible. And this sort of proof, so here when P is equal to 1, you can do this using DGA techniques. So differential graded algebra, again, thinking holomorphic curves, complex algebraic geometry. And I just kind of put a rough outline. So the idea is you have this algebra, I'm not going to go into what that is. If you look at the 2 copy of one of these unknots, the 2 copy will have an augmentation, a unique augmentation. And then you can look at 3 copies of the 2 copies. It's fairly complicated, but you can look at these characteristic algebras. And one of them has 0 divisors and the other one does not. And so that's how you can show that non-cyclic permutations are not possible. So if they were the same, they would either both have 0 divisors or both wouldn't have 0 divisors. Yeah, this is Chekhanov-Eliashberg DGA, but actually it's a little bit more, it's more than that, so it's kind of like a characteristic algebra, sort of, yeah. So it's not just, you start with a DGA and then you do something else to it. You do kind of quotients of it to get this characteristic algebra. So this is something that when Jen was doing her thesis, we tried to generalize it. It's like, this should work for other P's, right? Let's go to P equals 2. And the number of augmentations just blows up because, it gets really big, really fast. And it's just crazy. We got into a case where if P is 2, then using a more modern formulation of some things, we could, this is after Gen, so maybe about 5 years ago, we thought, oh, Lenny Ng was realizing, oh, if P is 2, then you could do it also. You're kind of using more modern formulation, but not beyond P equals 2. Yeah, so it's a lot more than that. So when P is 2, I think it had a unique augmentation, but then there were they both had 0 divisors, but then you have to do something else. But yeah, in general, once you get away from P equals 1, the number of augmentations just goes huge. And then you're not just looking at the 2 copy, you're looking at the 3 copy of the 2 copy. It's just huge, huge, huge. Yeah. So the convex surfaces is what we use to prove all the results that I'm talking about today. So this was used also in the historical results when they classified the Legendrian Torus knots and Etnyre and Honda. They use this techniques. And yeah, so everything today is by convex surfaces. And this is a newer technique for me. So it's been really interesting to learn. So let me just say a little bit about people working characteristic. Okay, couple of you. Okay, so if you have a surface in a contact manifold, we have this characteristic foliation. And briefly, it's very powerful, but it's very delicate. You move the surface a little bit and the characteristic foliation changes drastically. But if you look at a convex surface, so this just means that there's a transversal contact vector field. So a vector field whose flow preserves the contact planes. And okay, it seems kind of mild, but these are generic. So, and what's really nice is that this transversal contact vector field is basically giving you like a perpendicular to your surface. And getting contact, we don't have a notion, there's no perpendicular in general, but this is kind of giving us a perpendicular. And this gives us a place to we get these dividing curves, basically where the contact planes contain the perpendicular. So where are the contact planes perpendicular? Those are your dividing curves. These are Legendrian, this is singularities. This is a Legendrian curve, this is a Legendrian curve. And then, so the foliation itself is flexible, but like the Legendrian ruling curves, you can imagine these are kind of just ruling curves here. You can always kind of put it in standard form. So you have these ruling curves. So these are sort of flexible by moving your surface. Those might change, but these dividing curves give you like, they're changing by isotopy when you're moving your surface through convex surfaces. So it gives us like curves to play with as opposed to a foliation, which is a lot more complicated. So let me just give you a sample of some of how we use the convex surfaces. So say I want to show that, how do I think of a positive torus link? So you can draw the front projection and say, ah, this is it, right? But that's not how we think of them. So let's just think of how do I think of the ancestor? Instead of drawing the front projection, how do I view it from the convex surface point of view? So I would start with a Legendrian knot with max TB of -1, make a tubular neighborhood of it, okay? And there's results convex. I can put this in standard form, so that means it has a nice foliation. So in particular, the boundary of that tubular neighborhood has dividing slope -1. And I can assume that the ruling slope is Q over P. Okay, so I can choose that. And then n of these ruling curves will be an ancestor. So the positive in these convex tori, the positive ones are sitting in these ruling curves. And there's a lot more flexibility in those ruling curves than the dividing curves. So how do you pick that neighborhood? That just can exist. Yeah, there's kind of like standard. Yeah, in some sense, you can think of it that way, right? And now let's just say, okay, how do you see you can do arbitrary permutations? The big shift, right? The positive ones, you could do arbitrary permutations. Well, we know that these ancestors are living on this convex boundary, and there, in fact, will be an invariant neighborhood of that torus boundary. It's invariant in the -1, so that means that the contact planes aren't shifting when you move in that direction. And so what you see is it'll mimic the proof in topology. Like you have a torus link, I just kind of pull it off. If I wanted to permute the components, I would just kind of pull it off the torus, different heights, permute how you want to put it back down. It's exactly the same idea. So now because you have this invariant neighborhood, you just push it to a different, you just take the components, you move the components to different tori, you move them through the ruling curves. So you have this one parameter, the ruling foliation gives you a way to isotope there, and then you just push them back down to the torus. In the fact of how we constructed the ancestors. So when Q is positive, these are, you'll see these in the ruling foliation. When Q is negative, they're going to be in the divides, the Legendrian divides. You can see, yeah. So here, okay. So here, how do we see that? So it was all about how you realize the max TB, the ancestors. So if I wanted to do the negative torus links, how do I realize an ancestor there? So first I choose an unknot. Again, these are living on like unknotted tori. But now I choose an unknot with TB equals -m, where m is, again, you take your slope, your minus q over p, you sandwich it between two integers. I choose an unknot there. And then inside a standard convex neighborhood, there exists these basic slices. So I'll just give you a flavor. So if you're familiar with I always think of a very, a basic slice as a geodesic, a signed geodesic in this very tessellation. So here, this mouse really doesn't pull. Okay, so here you, so the basic idea is, you kind of think of one of these arcs as being your basic slice. So this is giving you M, and then there's two choices. So you have 2M. And then in this slice, which is basically a T2 cross I, there's going to be a pre-Lagrangian torus of slope minus Q over P. Okay, so this just means that you have this non-singular foliation. And choosing n of these lines will be your ancestor for the Q negative case. So it's these are much more rigid, these pre-Lagrangians, as opposed to seeing them in the ruling foliation of a convex surface. So, yeah, so it means exactly this. It has a non-singular foliation. Yeah. No, so they're still in the, in the dimension, it doesn't really make sense to say Lagrange, but right, yeah, right. But yeah, so it's just this pre-Lagrangian. Okay, a few more minutes. So let me just kind of outline, just give you a flavor of how you can prove. And again, this is really the part that took us like forever, for many years, many years to fill the gap. So, but the idea, okay, so here's just an outline of the convex surface argument. So we know that this ancestor lives on a pre-Lagrangian in a basic slice. So the first big step, and a lot of this is just low dimensional topology arguments. We kind of argue that if I could permute in R3 or S3, then in fact, you can do this in this basic slice. Again, a basic slice is just T2 cross I, so just kind of in a thickened torus. And then more low dimensional topology arguments, contact topology arguments. We can argue that this basic slice, you can represent, you can do a dimension reduction. Just see it, it's A cross S1, where everything is invariant with respect to S1. So my three components are now just represented by points. So I just repeated the above steps. So the step is here. So if I could permute these components, okay, so if there was an isotopy that took the two to the fixed one, you know, or kind of after what, you're like, at the end of the isotopy, 1 goes to 1 and 2 goes to 3 and 3 goes to 2, swapping those two. You can show that, well, there would be invariant neighborhoods of these components. And basically it comes down to finding that we could find this punctured annulus, where in one sense, there's a dividing curve that connects the 1 and 2 components. And the other case, there's a dividing curve that connects the 1 and the 3 components. And this is something that violates like this uniqueness of minimizing configurations. It's a result of Honda when he was classifying tight contact structures on surfaces cross S1. So again, we're using the rigidity of these dividing curves in a way to show that you cannot do a non-cyclic permutation. Okay, so just closing. So hopefully you'll take away that these torus links and cable links, so sometimes they're very flexible. They behave like what you would see in the smooth world. You know, sometimes you can do all permutations, but sometimes you can't. And so I've always enjoyed that about the symplectic and contact world. And that this convex surfaces are actually really quite a powerful tool, you know, just showing both that things are equivalent and non-equivalent. So this has appeared, it's on the archive right now. So this paper, if you're interested, getting more details. And thank you, that's it. Good question, yeah. Mhm.
How do you check that when, like, for these realizations,
Right.
From these particular convex surfaces, like how do you know that
Yeah. There's kind of ways, there's lots of things like if I have like a ruling curve, there's formulas that tell you what the TB of that is in terms of by how it intersects the dividing curves. You know, there's formulas here that will tell you what.
Like, I guess you're saying like maximum just means like maximizing in the Thurston.
Yeah.
In terms of classical invariance. So it's
right.
not like, okay.
Yeah, you're just maximizing the classical invariance, right? You can just check. Yeah.
Okay.
Mm-hmm. Yeah. Yeah.
So if you have, if when you're like doing all this classification stuff, I mean, are
Right.
you mostly using the convex surface theory to classify the maximizers, or are they also useful for classifying? Or I don't know. I mean, I guess maybe the whole problem is just you always reduce it. I'm just trying to understand.
Yeah. Again, there's a lot of arguments you have to show that that every representative will destabilize to one. So you have to figure out that these are ancestors, you know, so there's a lot of arguments to first show the ancestors. And then, but most of the hardest work is about doing it with the max TB version, or at least the ancestors, if you understand the statements there.
Yeah, like
so that's okay.
Every ancestor realizable by this like convex surface.
Yes, all ancestors are realizable by convex, and even all the like, not even the ancestors, but all of them can be realized as convex surfaces. Even the stabilizations. Yeah, you can realize all of these. Again, in the front projection, before I really started to work with, I would think of the knots in terms of their front projections with this, but then once you think in this way, you don't think of them that way. You think of them as these curves and these foliations, you know, are they ruling curves? Are they, you know, what kind? They're on a torus. What's the dividing slope of that torus? You know, as that changes, the TB will change and things like that. Yeah. So all of them, not just, I just emphasized here to give you a sample, the ancestors of how you think of them, but all of them can be thought of as curves, you know, in terms of this characteristic fully, you know, the convex surfaces, you know, curves there. Yeah. Yeah, it's really interesting. Very different way of thinking. Yeah.
So when we were doing like these problems, we were not. You said at some point that the DTA Convex Surfaces
Mm-hmm.
so that has like holomorphic hydrogen.
Mm-hmm.
The things that you're doing later,
Mm-hmm.
are there some holomorphic structure in there, or
But there are, but it's hard to quantify. Yeah. Yeah, in some sense, yeah. So, I mean, yeah, none of the classification of those are using holomorphic curves. They're all using the convex surfaces, you know, like those basic knot types. So is that what you're asking, sort of, or? Yeah, can you? Okay, sure. Maybe that would be good.
Thanks for dealing every single time we have a problem.
Oh yeah, no, that.
Like I got here like 30 minutes early. It's still,
Sorry.
it's okay.